Hey everyone, welcome to this Masterclass Explainer. We are absolutely thrilled to have you here today.
As an engineer, you're going to find that universal physical laws are exactly the same whether you're designing a system out in the scorching Sahara Desert or up on a freezing, high-altitude research station.
Right, but a truly exceptional engineer doesn't just memorize the physics. They know how to adapt those idealized equations to messy, real-world climates, and honestly, to incredibly strict international compliance codes.
Exactly. So today, we're bridging that gap. We're taking theoretical physics and translating it into field engineering. Let's dive in.
First up, we'll cover the physics foundations and limits. Then we'll look at market technologies and global codes. After that, we'll walk through a step-by-step mathematical simulation together. And finally, we'll wrap up with system integration and safety.
All right, let's jump straight into part one, the global physics foundations and theoretical limits. So, to master the macro-level electrical grid, you've really got to master the micro-level mechanics first. We're starting right at the atomic level. To convert sunlight directly into DC electricity, we rely on the photovoltaic process. For a photon to actually be absorbed by a silicon crystal lattice, its energy has to overcome the material's specific band gap limitations. And when it does, boom, it excites an electron, creating what we call an electron-hole pair. But here's the catch. What happens if a photon hits the cell with way more energy than that band gap requires? Well, that excess energy doesn't become electricity. It's immediately lost as heat through a process called thermalization. Right. And once we actually have those free charges, we've got to stop them from just randomly recombining. We do that by chemically joining p-type and n-type silicon to create a p-n junction. This interface forms a depletion region with a massive built-in electric field. You can think of this depletion region like a directional molecular slide. It forcefully sweeps free electrons toward the negative terminal and holes toward the positive terminal, and that is what creates a usable, open circuit voltage. Have you ever thought about why pristine laboratory physics can actually be pretty dangerous if you just blindly apply it out in the field?
It's such a critical oversight. Look, when you buy a solar module, the manufacturer gives you a nameplate rating based on standard test conditions, or STC. That assumes a perfect, uniform irradiance of 1,000 watts per square meter and a cool, artificially controlled cell temperature of exactly 25 degrees Celsius.
But out in the real world, under the blazing sun, panels get extremely hot. And that brings us to the nominal operating cell temperature, or NOCT, which usually sits much closer to 45 or 48 degrees Celsius.
The crucial takeaway here is this: as an operational cell heats up, its internal atomic lattice vibrates more intensely. This increases parasitic losses and severely degrades that open circuit voltage we just talked about. If you engineer a system using only those pristine STC lab numbers, your entire array is going to drastically underperform the second summer hits.
Let's move right along to part two, global market technologies and compliance codes. Understanding that physics directly allows us to pick the exact right technology for our specific global market. Just look closely at the temperature coefficient for monocrystalline silicon. It's the global workhorse, highly efficient at 20 to 24%, making it perfect for space-constrained rooftops.
But notice the catch there, it loses about 0.35% of its voltage for every single degree it heats up past 25 degrees Celsius. Now compare that to thin-film cadmium telluride.
Exactly. It has a lower overall efficiency, sure, but its temperature coefficient is far superior at just negative 0.21% per degree Celsius.
So, if you're a globally competent engineer designing an array for an extreme heat environment, like the Middle East or the Australian outback, you have to dynamically adapt your design. You'd select thin film because it will actually outperform crystalline silicon when those ambient temperatures skyrocket.
Once we've selected the panels, we have to actually architect the power network itself. Your balance of system hardware choices hinge entirely on local infrastructure reliability.
Right, if you're in a highly developed area with a stable grid, you'd build a grid-tied system. This basically uses the commercial utility network as a massive infinite buffer.
Conversely, if you're designing, say, an agricultural pumping station in a remote region, you build a standalone off-grid architecture. Now, that requires massive oversizing and total reliance on high-cycle lithium battery chemistry.
Bridging that gap, we have grid fallback, which prioritizes localized storage and really only taps the grid when the batteries run low.
And finally, modern hybrid configurations. These use multi-port inverters to fluidly route energy in both directions, actively executing peak shaving to avoid expensive commercial energy tariffs.
But here is the absolute life or death compliance reality that you must respect as an engineer. If you design a standard grid-tied system, you cannot provide backup power to your client during a blackout.
Why?
Because of a mandatory global regulatory code called anti-islanding protection. Your grid interactive inverter utilizes a phased locked loop algorithm to constantly track the utility waveform.
If the central utility grid fails, your local solar array absolutely cannot continue pumping power into the local grid. That would backfeed high lethal voltage onto dead utility lines, directly endangering the network technicians who are out there trying to fix the outage.
The inverter must actively detect the failure and mechanically disconnect within milliseconds. No exceptions. It is absolutely non-negotiable. Okay, let's get into part 3, a cooperative, step-by-step mathematical simulation. All right, class, grab your notes. It's time to get our hands dirty with a live, Chalk Talk style calculation. We're going to size the energy storage core for an off-grid 48-volt environmental telemetry station. Step 1. We never simply match the battery size to the load. We must calculate the battery sizing factor, or BSF. For this example, our engineering criteria demand exactly 1 day of total off-grid autonomy.
But we have to protect the internal chemical structure of our lithium battery bank. Deep cyclic draining causes permanent degradation, so we strictly limit our maximum depth of discharge to 80%, or 0.80.
Executing the math here. 1 day of autonomy divided by a 0.80 depth of discharge gives us a structural battery sizing factor multiplier of exactly 1.25. Step 2, we safely scale our consumer load profile. Our telemetry station requires a continuous, non-stop AC load of 24 kilowatt hours per day.
We take that 24 kilowatt hours and multiply it by the 1.25 BS safe safety buffer we just arrived.
This results in a minimum raw storage capacity of 30.0 kilowatt hours. By mathematically building in this buffer, we ensure the system survives an overcast day without crossing that catastrophic 80% discharge boundary. On to step 3. This is where we translate this raw mathematical energy into a real, physical, code-compliant hardware procurement blueprint. Our inverters and charge controllers run on a 48-volt DC bus, so we take our 30 kilowatt hours and multiply by 1,000 to get 30,000 watt hours. And we simply divide that by our nominal bus voltage of 48 volts, which gives us our final engineering specification, 625 ampere hours. If you followed along with the exact mathematical derivation in your notes, well done. You now have a specification that will confidently pass a strict professional engineering review in any jurisdiction. But before we leave the math behind entirely, I have a quick question for you. Have you ever considered what happens when the edge of a passing cloud perfectly magnifies the sun?
Ah, yes, the cloud lens effect. It's a vital, and honestly often surprising, environmental derating metric. It causes sudden, localized solar irradiance to spike well past that standard 1,000 watts per square meter.
To ensure your expensive maximum power point tracking charge controllers don't literally melt under these sudden thermal stresses, international electrical codes mandate a strict 1.25 safety multiplier on your continuous charge current. Bottom line, always oversize your regulators. Bringing us to our final part, Section 4, Real-World Networks, System Integration, and Compliance Safety. Okay, so we have the physics, we have the hardware, and we have the math. Now, we really need to address the real-world operational headaches that pop up when we integrate these parts into a live dynamic distribution network.
Take a phenomenon called the relay chatter loop. If you design a grid fallback system, you're relying on an automatic transfer switch. When a heavy industrial motor kicks on, the battery bank undergoes intense chemical voltage sag.
If your fallback system triggers based on a single, static low voltage point, the transfer switch instantly flips to the utility grid. But wait, the moment the battery load is relieved, its voltage instantly rebounds back to a normal level.
Right, so the system gets tricked. It thinks the battery is fully charged, and it switches that heavy load right back on. This triggers an infinite, violently rapid loop of mechanical relay switching that will absolutely destroy your equipment.
The solution? A clever engineer programs widely spaced hysteresis control loops. You set one extremely low trigger for the fallback and a completely separate, much higher voltage threshold before the system is actually allowed to recover. And what happens when a full utility blackout hits a hybrid system? A phenomenal automated sequence has to trigger in literal milliseconds. First up, island isolation. To satisfy those anti-islanding laws we discussed earlier, the internal grid relay mechanically snaps open, physically decoupling your property from the dead utility network. Second, load separation. Your battery bank just can't support heavy air conditioners or industrial heating elements during an outage. The distribution board split, purposely dropping the non-essential heavy loads. Third, EPS activation. The inverter instantly transitions into off-grid backup mode.
It creates a pristine sine wave with exceptionally low total harmonic distortion to flawlessly maintain your essential critical circuits. But here is a strict warning for you as future engineering peers. When that hybrid inverter decouples from the commercial grid, you lose the utility's centralized neutral earth reference point. And if there's a short circuit to a metal appliance chassis while you're running in isolated backup mode, the fault current will have no return path. Your overcurrent breakers will simply not trip, leaving an exposed metal frame energized at lethal voltage. This is exactly why you absolutely must ensure that advanced hybrid topologies feature an internal automatic ground signal relay. The moment the grid drops, this relay closes, building a localized temporary neutral earth bond right at the property. This guarantees that your protective residual current devices, your RCDs, still trip correctly and, most importantly, safely protect human life. And that brings us to the ultimate question. The laws of physics, the photon absorption, the band gaps, the depletion regions, they're never going to change. But the environment, the grid codes, and the structural constraints, they always will.
As a globally competitive engineer, armed with the rigorous mathematics and systems knowledge from this masterclass explainer, how will you adapt these universal physical laws to build life-saving, universally compliant, and incredibly resilient energy networks in your region?
The tools are in your hands now. Go design the future.